Hello everyone, I'm Donghyun Lee from Seoul National University. Today I'm going to present my work called Frugal 3D point cloud model training via progressive near-point filtering and fused aggregation. This work is done with my colleagues at Seoul National University under the advisement of Jae Lee and Hong-il Yoon. Recently, following the success of PointNet and PointNet++, deep neural networks have been actively applied to 3D point clouds. Various ideas have been proposed, continuously enhancing the model performance and computational efficiency. However, the rapid growth of 3D point cloud models and datasets have led to significantly higher training costs for 3D point cloud models. PointNet-based model is composed of four major operations: farthest point sampling, ball query, MLP, and aggregation. We have conducted an in-depth analysis on PointNet-based model training and identified that the two major performance bottlenecks are farthest point sampling and aggregation. To address these bottlenecks, we propose two techniques called Lightweight FPS and fused aggregation, which reduces redundant computation and memory accesses present in FPS and aggregation. First, we look at farthest point sampling. We make two key observations by examining FPS from a training perspective. First, since the coordinates of the input points do not change throughout the training process, redundant distance calculations of FPS are performed for the same input every epoch. Original FPS ensures randomness of the sampled points across epochs by repeatedly performing FPS for the same input with different seed. Second, from the point spacing distribution of farthest sampled points, we observe that the key factor in achieving high-quality sampling is to ensure a minimum spacing among the sampled points. Furthermore, since we target FPS operation in the training process, we can easily calculate the threshold value in advance by simply performing FPS once before training with negligible cost. Based on these observations, we propose lightweight FPS via progressive near-point filtering. First, we perform FPS once to find the minimum spacing between the farthest sampled points. Then, we perform a ball query with each input point as a centroid to identify points within the specified threshold proximity. The indices of the identified points are then saved to the filter matrix. Finally, points that are sufficiently close to the previously sampled points are filtered out every iteration by referencing the filter matrix. After filtering, we randomly select a point that remains unfiltered. Through this algorithm, lightweight FPS can maintain good sampling quality while also preserving enough randomness across epochs. Next, we look at aggregation. The forward pass of aggregation is composed of grouping and max reduction, while the backward pass requires scatter and sum reduced operation. We observe that there are redundant memory access to the intermediate values in these operations. Furthermore, we observe that ineffectual computations are performed during the sum reduction in the backward pass due to the high sparsity of the scattered gradients matrix. For example, two gradient P3 vectors are gathered and summed in this figure, even though this is an ineffectual computation with zero values. Based on these observations, we propose fused aggregation. Grouping and max reduce operation are fused into a single GPU kernel, eliminating memory accesses to the intermediate values. We then save extra information that tracks source index of input point features for the selected maximum element. In the backward pass, gradients are directly scatter reduced according to the source index table. Through this strategy, Redundant memory accesses to the intermediate values are removed, reducing ineffectual computations on those values as well. We apply our techniques to state-of-the-art PointNet-based models and evaluate the performance on NVIDIA RTX 3090 GPU. Our experimental results demonstrate 2.25x training throughput improvement with no impact on model accuracy. Thank you for listening to our talk. Please refer to the full paper for more details.